Hey, Dr. B here, and let's take a look at chemical bonds and forces. Here's a look at a couple of viewpoints of diamond, one of the strongest chemical bonds you can form, perhaps the strongest. We deal with these individually as networked bonds, and there's several types. You can have a network covalent bond, for example, in a diamond, which is shown here. Now, this is not just this many atoms, as you see here. It's completely networked throughout the lattice, and this is another viewpoint of it, where the strength can approach 5,000 kilojoules per mole. Similarly, an ionic bond is a continuous lattice, but this time between positive cations and negative anions. Still, the strength can be up to 4,000 kilojoules per mole between that sodium cation, for example, and that negative chlorine anion, an electrostatic plus to minus attraction. A metallic bond, no, metals can be very strong. This isn't to say that they're unreactive, right? These will tend to oxidize, tend to lose electrons. And yet, the bond, even in its atomic state, can be quite strong, up to 500 kilojoules per mole. All three of these types of bonds are continuous lattices where you're not going to see the dashed lines that represent individual intermolecular forces. An intramolecular bond is a classic covalent bond, such as exists between two carbon atoms. These would have absolutely the intermolecular forces between them, and if it's one like this, it's not going to be much. But that covalent bond right there can still be over 1,000 kilojoules per mole. Let's bring it down to real intermolecular forces. So now we're dealing with bonds up here and forces down here, and I thought it's useful to present the entire continuum here so you can see where a bond might end and an intermolecular force might take over. The strongest type is that between an ion and a dipole. After all, if it was an ion-ion, that would be a formal ionic bond. But if it's just between an ion and something that has some polarity to it, meaning two different atoms bonded, for example, hydrogen to oxygen, here's your positive part formally, here's your negative part partially, and that can form a bond that can give you 600 kilojoules per mole of energy. And I shouldn't say bond, I should say an intermolecular force. See the dashed lines? That would be between two substances there. A hydrogen bond force is also quite strong, and it's just a case where you have a dipole-dipole, two things with polarity. But if it's nitrogen, oxygen, or fluorine connected to a hydrogen, that is particularly electropositive for hydrogen and particularly electronegative for either fluorine, oxygen, or nitrogen. Attract that to anything with a lone pair, and you've got a pretty strong force of attraction. We don't call it a hydrogen bond, at least I don't, because it's not a bond. It's an intermolecular force, so I want to make sure we're differentiating there. And we can get up to 200 kilojoules per mole, and here it is between two water molecules. That's your partial positive, that's your partial negative. If it's another dipole-dipole force, but not involving this kind of a unique situation, for example, between the electronegative oxygen and carbon and the electropositive carbon and carbon dioxide. These are two carbon dioxide molecules. That can be up to 25 kilojoules per mole. We're getting a lot weaker now. And the weakest, typically, intermolecular force is called a London dispersion force or a van der Waals force, and that can involve even identical atoms or molecules that are interacting with each other. And you might ask yourself, well, what's the attractive force? Well, there's barely anything, but the idea is that at any point in time there might be an uneven sharing of electrons, so you get a temporary dipole, and look at how weak it is. It can be a 20th of a kilojoule per mole, for example. Those are present between any two atoms or substances. So those are your intermolecular forces. And let's have a look at these questions. See if, based on what you've learned here, you can answer these. Suppose an ionic bond breaks, like this one right here, but it's not forming new bonds. The only way that can happen, that sodium cation, that chloride anion, are not going to be hovering around. I suppose it's possible they're to be in the gaseous form, but that seems just crazy to me. Much more likely it's dissolved, right? That's what happens when Salts are thrown into water typically, as long as they are soluble. And if they are in solution, but then the ionic bond reforms, well, it must have precipitated. If you have no intermolecular forces at all, there's only one case I can think of where that's the case, and that's when you have a gas. If they are fixed, we call that a solid. If they are fluid, we call that a liquid. There's a huge difference in the boiling point between hydrofluoric acid, which is just about room temperature, just a little below, and HCl, which is almost always a gas, right? I've never seen pure HCl get liquefied. Boy, you'd have to go really, really cold for that case, or high pressure. And in this case, the reason is because, as we've shown before, hydrogen fluoride is right there. That would be H to F. If it's connected to something with a lone pair like fluorine, you've got a hydrogen bond, particularly strong dipole-dipole interaction, and only HF has those H bond forces. Now let's take a look at some, say you've got a fair amount of any of these substances. Let's consider the strongest intermolecular force. Not much for two nitrogen molecules, just London dispersion forces, since they have equal polarity, right? Each nitrogen in a nitrogen molecule shares those electrons evenly, but not necessarily always. Carbon dioxide, I see a dipole between carbon and oxygen. Sometimes people get confused here because it's true that carbon dioxide is considered a nonpolar molecule because it's linear and the oxygens are at opposite ends from each other, so the charges cancel. But certainly carbon is electropositive and oxygen is electronegative, so you can form a dipole-dipole force there. Water, as we've seen before, can hydrogen bond, so we have a hydrogen bond force there. Same for HF. Methanol, I do see O to H, so if that connects to another lone pair, like the oxygen in another methanol, we've got a hydrogen bond force there as well. Carbon tet can't do that. That's carbon tetrachloride, but it can form a dipole-dipole since carbon is more electropositive than chlorine. Which bonds must be broken to melt it? So have a look at all these things, and this is another sort of can you answer it kind of thing. Guess what each one of these things is, and then think about what it might take to melt that substance. We're going to start off with diamond, and I don't know if it's even possible to melt a diamond, but at least we know what the strongest intermolecular force would be. And it's the same as the intramolecular bond since it's a complete lattice. And that would be the network covalent bond. If we have a chunk of a metal, this happens to be iron, well, we've got to overcome that metallic bond to melt it. And certainly that's possible, right? Foundries and things like that, they have to melt those metals. Some of them, it's true, can exist as a liquid at room temperature or just above. We've got a pile of iron oxide. Those are ionic compounds, so we would have to overcome the ionic bond in order to melt that stuff. And that's going to take a lot of energy. Look at these temperatures here. If you consider that a flame might hit 600 degrees or so, these things are very high melters, as is sodium chloride, also known as table salt. We'd have to overcome that ionic bond to melt it. Molten sodium chloride is possible, as is glass. You can melt that. This is silicon dioxide, a nice crystalline form of glass, if you will. We've got to overcome that network covalent bond. You might have guessed something else for that, but I guess that's partly memorization. Silicon dioxide forms a network covalent lattice. Not so with a pile of sulfur. Notice that we do see the S8 here. So this is a octahedral complex. So if you draw an 8-membered ring, it would look something like that. And between two sulfur molecules, well, I'm thinking identical polarity, right? Identical. So the best we could do is a London dispersion force. But I can imagine, since it's 8 of them in a ring and it's sulfur, we could have pretty strong London dispersion temporary dipoles, I guess. I think I'm trying to justify that relatively high melting point there. If you've ever worked with a chunk of sodium, you almost never think about its physical properties because exposed to almost anything, it tends to react. It's typically stored in oil or under an inert gas. But the pure sodium, if you can get it to stay, now we're talking about overcoming that metallic bond in order to melt that stuff. And it's above 200, although it's quite soft. Water, that is one everybody should be familiar with. It's going to melt at 0 degrees, and we're overcoming those hydrogen bond intermolecular forces. Got some booze, in this case some grain alcohol. We'll say it's pure ethanol. Very low melting point, right? Even if you throw it in the freezer, that will still be a liquid. However, it can hydrogen bond. The rest of it, though, this tail, if you will, can only do London dispersion forces. Now we're dealing with some pure hydrocarbons. You're not going to do better than London dispersion forces for either of those, and look at those very low melting points. Okay, this is an overall look at chemical bonds as well as intermolecular forces.